Hi, I'm Jonathan Aldrich. Today, let's talk about the semantic properties of languages, in particular soundness. As we discussed before, static and dynamic semantics are really designed to fit together. If a program passes semantic analysis, then the conclusions of the semantic analysis will hold when the program runs. This property is known as type soundness. It tells us that we've designed our static and our dynamic semantics so that when we do a static semantics, we can trust the results when we run the dynamics. So we can actually state a theorem, type soundness for expressions with variables. If we have an expression E and it type checks in some statement gamma and at type tau, and there's some environment E of mapping variables to values where that mapping matches gamma. Basically, this says that for every variable x in the mapping gamma, that variable also appears in E, and it has the same type that it has a value of the type that gamma gives it, right? So it just tells you that this environment kind of makes sense with respect to the assignment of types to variables in gamma. So you got to have an expression that type checks. It type checks in some gamma, and we have an environment that matches that gamma. Then we can take that environment and evaluate that expression down to a value. Then that value should have the proper type. So that's just a way of formalizing this statement, or this intuitive statement, that the conclusions of semantic analysis or type checking hold when the program runs. And so we see this theorem has both our judgment for type checking and our judgment for evaluation in it. Our simple calculator language has an additional property. Any expression that is well typed is guaranteed to terminate. Now, if we had a more interesting language with loops or with recursion, this wouldn't actually be true. But it is true of our simple calculator language. There's a related property called progress that holds even for languages that are more complicated than calculator. I won't talk about that today. Let's just look at termination. So the termination statement is similar to soundness. It starts out the same way. If we have a program or an expression that type checks at some type tau, and it type checks in some environment gamma, and we have some concrete execution environment E that matches that gamma, right? Basically, all the variables in E have values of the types that they're given in gamma. Then we will be able to evaluate E down to some value for that value. So what the theorem means is that the execution will not end in a runtime error if the original program is well typed. Okay, so remember that end in a runtime error, basically we're formalizing that in our system as not being able to apply the evaluation rules. As I said, more sophisticated languages are not guaranteed to terminate. Some runtime errors may still happen, but in a sound language, such as the Java language, runtime errors will not occur except in well-defined places, like programmer-inserted casts. And so there's a way of stating a similar theorem for languages like Java that help us ensure that our type system and our execution are well aligned. So the two theorems that I showed you, as well as a third theorem that's stated in the book, can be proved using mathematical induction. Roughly speaking, what the proof does is it inductively evaluates the typing derivation. It looks at one rule at a time in the typing derivation and reasons about how the typing of this expression will match the execution when the same expression executes. Basically, the typing derivation will line up with the execution derivation. And so for each typing rule, we show that the typing rule, together with assumptions from the premises, which come from the induction hypothesis, basically we assume that if the premises are well typed, then that execution of that expression will terminate, and then it will have the right type. And so based on those assumptions, we can prove the soundness or termination property of that rule itself. So that is a little bit of a mouthful, but some details are given in the text. Have a look at it, and you can see how we can mathematically guarantee that, how we can mathematically verify, I should say, that our definition of our runtime rules in dynamic semantics matches the definition of typing rules in such a way that type errors won't happen when we execute the program. Let's check our understanding. Let's summarize what we've learned in our discussion of semantics. Semantics defines the meaning of the language. The dynamic semantics defines how a program executes at runtime, whereas the static semantics define how we type check and perhaps how we transform the program to optimize it. Both static and dynamic semantics and transformations can be made precise using mathematical inference rules, which is why we've talked about a little bit of formalism in the last few lectures. Well-designed semantics are nice because they have strong theoretical properties, such as soundness, that have concrete benefit to programmers. They ensure, for example, that certain runtime errors cannot occur as long as we've type-checked the program. It turns out that careful design of semantics and proof of soundness can ensure the safety and security of languages like Java and of platforms like WebAssembly, and they're very important to the engineering of languages today.